Welcome to section 3.3, Properties of Logarithms. We've introduced exponential functions and simplified some of those. We've also done logarithms, but now we're going to move on to properties of logarithms and be able to start solving logarithmic equations. We need to evaluate and rewrite logarithm expressions just to kind of practice the properties, and then we'll get into solving logarithmic equations. First thing is properties of logarithms. If you take a look at this kind of definition that we're kind of looking at, or property that we're looking at, it says let a be a positive number such that a cannot equal 1, and let p be a real number, and m and n are positive real numbers. So when we look at that, kind of a lot being said there, and what is it that we're actually talking about? Well, I want you to kind of look back actually at our exponential definition the other day. So an exponential function, f with a base a, is denoted f of x equals a raised to the x, and we had these stipulations, and we talked about these in class. Why a must be greater than 0, because if it's not, it's going to jump back and forth like I was showing you over here. Alright, a can't equal 1, because if it equaled 1 it would just be a horizontal line, and you can plug any number you want in for x. So now to kind of jump back to what we just talked about, remember logarithms are inverses of exponential functions. So when we look at this property of logarithms, let's kind of think back to what we were just saying there. Well, let's do this on the next slide. You can see is if we say a raised to the x power is equal to y, or I'll write it the other way, y is equal to a raised to the x, and we said a cannot equal 1, alright, and a must be greater than 0. We also talked about x being a real number. And the other thing is, what outputs do you get when you do this? Well, if a is greater than 0 and not equal to 1 and x is a real number, then your y value, your output, will be values that are greater than 0. And we even saw that on the exponential function. Okay, so now what happens when we look at a logarithm? Well, I'm going to rewrite this as a logarithm. So this would be log base a of y equals x. And so now that a value is the base of the logarithm. So it still is true that a cannot equal 1 and a must be greater than 0. And that's what that first statement says. It says a is greater than 1, or greater than 0. It's a positive number, and it cannot equal 1. Okay. So then what else? Well, the y value, or let's do the x value. The x value is all real numbers. So this logarithm, remember what we said, logarithm is an exponent. This is the exponent, alright, and the exponent for the exponential was all real numbers, so that value, our end result, can be all real numbers. But what about the y value? And take a look, the y value that we were looking at right here is now right here, and we said that has to be greater than 0 because of what the other stipulations are on the exponential function. So the same thing has to be true for the logarithm. And so now if you go back and look, the values that we're talking about, we don't have them written as y, it's the m and n values. Those must be positive real numbers, and a lot of times in logarithms those are the values that we're actually solving for. So now when we're solving equations, we have to be aware that if we get solutions that create negative numbers for these values, or 0, then they're not going to be real solutions. They're not going to be solutions that actually work. So that's the first thing. No kind of a lot of explanation there, but I do think it's important. Kind of the next thing to look at is, let's take a look at these properties. Log base a of mn, m times n, you can rewrite as log base a of m plus log base a of n. And kind of the question for me is well, why? Why can you split those up with addition? Well, remember, a logarithm is an exponent. When do you take two exponents and add them together? We did this the other day. X raised to a times x raised to b. Well, I guess I'll rewrite it now. So x raised to a times x raised to b. What do you do with the exponents? you add them. So look what's happening here. You're adding the exponents. And when you add the exponents, what is actually happening? You're multiplying. And look what's going on right here with those values. You're multiplying. So with a single logarithm, if you're multiplying, you can split it up into addition because that means you're adding the exponents. So maybe that makes a little bit more sense in terms of why you're able to do that. Same thing with division. If you had x raised to the a divided by x raised to the b, what did you get? X raised to the a minus b. So when you're dividing, you will now be subtracting. So you're taking a single logarithm and splitting it up into two logarithms. We also have this one. This is the we got the power property here, where you have a log base a of a number or a variable raised to a power, and what you can do is you can actually take that and move it to the front of the logarithm, which you see right there. Okay, so that really just gets moved to the front, and you get p times log base a of m. The 3 on the other side here, you have log base a of a equals 1, and really that's inverses. They cancel each other out. We'll talk more about that in a little bit, but log base a of a is 1, and really if you want to ask yourself the question, you're saying a raised to what power is going to give you a? Well, that would have to be 1. Same thing on this one. A raised to what power gives you 0? And that would be, whoops, I wrote that wrong, sorry. A raised to what power is equal to 1, and that would be the 0 power. So a to the 0 is 1. And then on the last one here, we have a logarithm equal to another logarithm. Alright, if a logarithm is equal to another logarithm, then these values will be equivalent. And I'm going to talk about why that actually works. So that M&M, I mean, it looks maybe pretty easy as to why it works, but we'll talk about using inverses, why that actually works. So let's go ahead and move on. A lot of explanation in the beginning, I know that, but hopefully it helps you kind of see everything here. So the first thing I want to do is really just practice this stuff. This is stuff that we're going to use to help us solve an equation. So the first example is, use the properties of logarithms to expand this. So by looking at this, we have log base 2 of two things being multiplied together. So we want to expand this out by using our properties. Well, since we're multiplying, that means that we can take the individual products there and we can add them. So log base 2 of 3x plus 1 plus log base 2 of x plus 1. And that's now expanded out. Alright, you're taking a single logarithm and expanding it out into multiple logarithms. The second one is a little bit more complex. There's a little bit more going on, so we'll do a couple different things here. We'll have log base 2, and maybe I should write this below it instead. So we'll have log base 2. You have division first, so we will have log base 2 of 5x to the 4th minus, since we're doing division, we'll subtract y to the 3rd. Alright, but now we can go farther. This one right here, this 5x to the 4th, that is log base 2, and since you're multiplying, log base 2 of 5 plus log base 2 of x to the 4th minus log base 2 of y cubed. And so you might think you're even done there, but now you have these exponents, alright, that you can move to the front. So we'll do one more thing here. We got log base 2 of 5 plus the 4 goes to the front, so 4 times log base 2 of x, the 3 goes to the front, minus 3 times log base 2 of y. So that's expanded out completely. So we took a single logarithm and turned it into 3 logarithms. So that's once again really just working on the properties, and we're going to do the same thing on example 2, but we're going to kind of go the other way. we're going to use the properties. Instead of expanding, they're already expanded out, and we're going to simplify. And this is really where we'll start to use this idea to solve equations. So when you look at 2a here, you got 3 log base 4 of x plus log base 4 of 5 minus 7 log base 4 of x. Well, with logarithms, when these numbers are out front, you can't use those properties for the product and quotient rule. And you're going to have to do something with those. Well, the only thing that we can do with those is move them to the power of the value of x in this case. So this is going to be log base 4 of x cubed plus log base 4 of 5, that one stays the same, minus log base 4 of x to the 7th. And now that we got those numbers out of the way, now we have a logarithm plus a logarithm minus a logarithm. So we'll do it in parts here. We'll do the first one is addition. So when you combine that to a single logarithm, you're taking an exponent plus an exponent. Remember, when you do that, you multiply. So this would be log base 4 of 5x cubed minus log base 4 of x to the 7th. And now you're subtracting. So you can combine one more time to get a single logarithm. That's log base 4 of 5x cubed divided by x to the 7th. Now, in terms of going from 3 logarithms to 1, we've done that. We actually can simplify this because we do have a common base here. So let's go one more step on this one. And this will be log base 4 of 5 over x to the 4th, because there's more x's on bottom. So 7 minus 3 is 4, and since they start on bottom, they stay on bottom with x to the 4th. So that's simplifying it in terms of getting to a single logarithm. Same thing on the next one, b. What do I need to do here? Well, we have this 1/2, and a lot of you might want to distribute that 1/2 in, which would be okay, but let's go ahead. It's kind of order of operations. Let's do what's inside the parentheses first. And since you're adding, that means we are going to multiply. And that 3 we're going to have to move to the exponent. And it's 2x here, so you're going to have to raise it to the 3rd power. So now we have 1/2 log of 5x minus log of 2x. So now what do? Well, we have 1/2 log of 5x minus log of 2x to the 3rd. So that's 8x cubed. This 1/2, once again, we're going to have to move it to the exponent. So it's log of 5x to the 1/2 minus log of 8x cubed. And then now we have subtraction, so we'll change it to division and go to a single logarithm, log, and then we have 5x to the 1/2. Now 5x to the 1/2, 1/2 is actually the square root, so I'm going to go ahead and change it to the square root of 5x over 8x cubed. And so there's your single logarithm. Can't do anything else at this point. And we didn't really notice, I don't know if you paid attention here, but these logarithms don't have bases. Well, if the base is not there, similar to when you see a square root, there's no number here, but it's a square root. It'd be a 2. With a logarithm, when you don't see it, it's actually base 10. So anytime you have a logarithm that doesn't have a base, it's base 10. Not base 0, it's not base 1. It can't even be those two numbers. Remember, that value has to be greater than 0 and not equal to 1, but it is base 10. Okay, so those are the properties of logarithms, and that's how you kind of use them. Now let's really get to really the main focus today, which is solving. So we're going to use these properties to solve. And so the first one we're looking at is log base 7 of 5x minus 2 equals log base 7 of 2x plus 7. Well, when you solve equations, you have to undo the problem. Well, how do you undo a logarithm? You undo a logarithm by using exponential. So I'm going to write this one out the first time, and we can simplify this a little bit later, but this is log base 7. So to undo log base 7, we're going to do 7 raised to log base 7 of 5x minus 2 is equal to 7 raised to log base 7 of 2x plus 7. So what did I just do? Well, I took 7 as my base, and I took those values, and those are now my exponents. But why would I do this? Well, because these are inverses. 7 raised to log 7, that cancels out, and you're left with 5x minus 2 is equal to 7 raised to log 7 cancels out, and you're left with 2x plus 7. Now, could I go straight from here to here? Sure. Alright, understanding that a logarithm equal to a logarithm, those values are going to be the same. But what I really don't want to see is this. And the reason I don't want to see that is because that's not really true. Those log base 7s don't just cancel out. You can't have, a logarithm has something more than just a base 7. Alright, you can't cancel out just log base 7. A logarithm has more stuff than that. So I don't want to see you canceling out these logarithms like that. If you're going to cancel them out, then you really need to show this second step here as to why they're canceling out. So anyways, we're going to use inverses to solve. So now we go ahead and subtract 2x to the other side, add 2, and get x equals 3. Now we know when we solve, there's always stipulations as to, sometimes the answers aren't, true or whatever. Well, do I need to check these? Well, what you need to check with is going back to the original and saying, this value that we're talking about, these numbers must be positive real numbers. And so when we go back to that slide, if x is 3, do I get positive real numbers up here? Well, 5 times 3 minus 2, is that a positive number? 2 times 5 plus 7, is that a positive number? And that's what we're looking for. So anyways, that's what you're looking for in terms of solving. So when you plug those values back in, do they give you a positive solution? Why did I put it? I was trying to figure out why I made a mistake, and that's not 2 times 5. 2 times 3 plus 7. And so on this one you would get 13, and on this one you would get 13. And so as long as those numbers are greater than 0, then they will be solutions. So we got to make sure that they are positive numbers. And so x equals 3 will work out. Now b is similar to a, but we got a little bit more to do here. First we have addition, alright, and maybe even before that we have this 4 in front that we're going to have to simplify. The first example gave you a logarithm equal to a logarithm. This is a logarithm plus a logarithm equal to a logarithm. So some of you might say, well, why can't we just use inverses, and we're going to say 2 raised to log base 2, 2 raised to log base 2, 2 raised to log base 2, and we'll just sit here and go cancel, cancel, cancel. Well, that's like saying x squared plus x squared is equal to 36. And I'm just going to take the square root of whatever I want because I can do that. Well, no, you can't. You got to keep things balanced. You can't take the square root on the left-hand side twice and the right-hand side once, and with the addition and everything else. It's the same thing with logarithms. All right, you can't just use those inverses wherever you want to. You've got to combine them to get a logarithm equal to a logarithm. So we're first going to move the 4. So this is log base 2 of x to the 4th plus log base 2 of 5 is equal to log base 2 of 405. Okay, that's a start. But now we have the addition. So what do? Well, we're adding logarithms, which means we're adding exponents, and when you add exponents, you multiply. So this is actually 5x to the 4th now is equal to log base 2 of 405. And so now we're back to kind of what the first one looked like, where you have a logarithm equal to a logarithm. So I'm going to show my work, but I'm not going to show that first step. I'm going to say, okay, we both have a base 2. So this is 2 raised to log base 2, and this one's 2 raised to log base 2. And so these are inverses, they cancel, and you're left with 5x to the 4th is equal to, those cancel, 405. And now you can solve that equation. Divide by 5 gives you 81. This is x to the to the 4th. And to undo that, you would be taking the 4th root of that, and so that will give you x equals, what's the 4th root of 81? And that would be one of those that you should know, and the 4th root of 81 is 3. Now it's actually plus or minus 3. Since it's even, you get positive and negative. Do both of those make sense? Well, you plug this back into the original, which is all the way up here. So can x equal 3 right here? Sure, that's positive, that's greater than 0. Can x equals negative 3 right there? No. That's log base 2 of negative 3. You can't have a negative value. So that one's out, which means your only solution is x equals 3 on this one. So you do have to do some checking on these equations. Alright, let's go ahead and get to the last one here. Solve the logarithmic equation here. Now this one, once again, you might see some similarities, but you also might notice a difference that on this one, we have a number on that side and not a variable. So what are we going to do? Alright, well, we have logarithm minus a logarithm. So that's division. That's log base 3. And then we divide. 3x plus 1 divided by x minus 1 is equal to 2. Well, now we're going to solve this one the same way, but you're going to see something a little different. To undo log base 3, we're going to do 3 raised to log base 3 and 3 raised to the second power. So it cancels here, and you're left with 3x plus 1 over x minus 1 is equal to 3 to the second power, and that's 9. So instead of the right hand side canceling a logarithm, it's just 3 raised to the second power. And then now you're back to solving. You can cross multiply by x minus 1. That'll be 3x plus 1 equals 9 times x minus 1. And at this point you should be able to be good to go. Distribute. I'm going to subtract the 3x, add the 9, and so divide by 6, and x is equal to, simplify the factor of 2 out, and that's 5/3. And so is this a reasonable answer? Is this an answer that makes sense if we plug it back in? Well, 3x plus 1. If you plug in 5/3, is that going to give you a value that's greater than 0? And it does. I have to figure out it's going to be greater than 0 because it's all positive. But on the other one, you have an x minus 1. If you plug in 5/3, is 5/3 minus 1 going to be greater than 0? Well, yeah, 5/3 is bigger than 1, so 1 minus 1, or 1 2/3 minus 1 would be positive. So it works as well on that one. So you're plugging it back into the logarithm to see if that value is greater than 0. So x equals 5/3 is our answer and our final answer. So there's going to be a lot of different solving equations that we need to look at, but this should definitely be a start to be able to see what you're doing in terms of solving and realizing that you're undoing the logarithms by using exponentials and using inverses to figure that out. Thank you.